So what I hope to achieve with this talk this afternoon is for geoscience audience. I am hoping to highlight from a practitioner standpoint which of these machine learning methods are making a difference to our everyday life and are making business impact. And for the more computationally oriented audience, I'm hoping to mention what's that we would like to see happen so that more of these algorithms do impact our everyday workflows. And before I leave this slide, I, of course, want to draw your attention to the engaging disclaimer at the bottom, which mentions that while I may be expressing strong opinions, and the talk wouldn't be interesting without it, it is a fast-paced area, so what is true today may not be true tomorrow. And in any event, what I say should not be confused with our official company policy. All right. So for those who have not had the chance to read it, you can see me after the talk, and I'll show you the rest of it. Since I wasn't sure what audience to expect, I'm going to start with a 2-minute introduction to the seismic method. Looking at how many faces I recognize in the audience, I'm not sure that's really necessary, but please bear with me just to make sure that no one's lost and everyone understands what I'm talking about. Then I'm going to give you a bird's eye view of machine learning applications to seismic processing and interpretation. And then I'm going to try and delve a little bit deeper into deep learning more specifically, and I'm going to highlight 4 different types of applications that we're utilizing, as well as mention along the way how we obtain training data, what challenges we're facing, and I will, of course, try and make sure that for each and every one of these examples, I emphasize what computational or HPC applications that particular technology has. And then at the end, I have a slide on what we view as some common technical challenges, and I'll leave you with a few take-home messages. So, like I said, please bear with me here for a couple minutes so that I can introduce what the seismic method is. And it's not too dissimilar to how bats echolocate their prey. They just send out a seismic signal, they record what comes back, they solve an inverse problem, and that allows them to determine where their prey are and what kind of prey that is. We do something very similar for seismic. In the exploration setting, we have a boat sailing along. It sends a sound pulse down into the subsurface. It gets reflected and recorded either on close to this air-water interface, or in fact sometimes down on the seafloor. I'll be talking about ocean bottom nodes later on. That's when receivers are on the seafloor. Of course, what's also important is that these reflections can bounce up and down multiple times, so sometimes we have to deal with so-called multiples. I will be mentioning them later. And as you can also see, we also image the subsurface, or we'll look at the reflections that have different reflection angles, as this picture indicates. And that gives us what's equivalent to a color photograph. So if we only illuminated the subsurface with a single ray, that would be like looking at a black and white photo. And because we have multiple angles, that's equivalent to having color in your image. And that, of course, has implications for machine learning, where we typically use multi-channel neural networks, which are used to seeing RGB, several channels of color, as input. Now, for land acquisition, it's not too dissimilar. The principle is exactly the same. You still send a sound pulse into the subsurface and you record it on the surface. Once we have acquired this sort of seismic data, we move on to performing seismic processing and imaging. And again, for the purposes of this talk, I'm going to oversimplify and say that seismic processing is mostly about noise attenuation, while imaging is mostly about determining the speed with which sounds propagates in the subsurface, and then using that to back project the sound waves that you have recorded at the surface back into the subsurface and form an image of the geology that you can see down there. And with that image in hand, we then do interpretation. Okay, so in just a tiny bit more detail, what you can see here is a typical what's called shot record, where you plot the waveforms that have been recorded on the surface. They're usually plotted as a function of time at which they arrived at the surface going vertically, and the distance between source and receiver going horizontally. And the trick is to make this look as clean as possible. That's what noise attenuation is about. Then we build a model, we backpropagate these sort of recorded waves back into the subsurface, and we form an image, which is again shown on the right. But that's where it gets exciting. Once we have this image, we start looking for various geologic features in it. For example, discontinuities like this one. You may or may not be able to see it clearly. It's called a fault. And then we also look for horizons, geobodies, and various other features in seismic. And the thing to remember here that's important for later examples is that seismic is inherently a 3D object. It's not a 2D image of cats and dogs, it's inherently 3D. And moreover, it can have more dimensions than that, because I mentioned a second ago, you may be obtaining images like this based on different reflection angles that you have recorded at the surface. So now I'm looking at the big picture, and I'm going to use some diagrams from this awesome paper with an awesome title that you can see at the bottom. And it just happens that their conclusions and observations coincide exactly with the impression I have as well as to how machine learning methods have progressed as they apply to seismic methods. So what you can see from this chart, again on a high level, is that there are extensive efforts in both seismic processing, and for the purposes of this talk, I'm going to lump imaging and inversion into that bucket as well, and interpretation. However, the difference is that while the number of overall publications, which is what this paper analyzed, is about the same, roughly speaking, on both topics, the majority of processing-oriented efforts come from academia. And as far as I know, there is a limited number of successful field data applications, while the majority of interpretation-related work, as you can see from this diagram again, comes from industry. And that in itself, I'll dare to say, tells you what works and what doesn't. Yet. So looking specifically at ML-assisted seismic processing, most of the work, again, just look at the diagram, and then it's from the same paper, is focused on velocity model building and pre-processing, which really means that people look at full waveform inversion, how to determine that speed of sound in the subsurface, and how to backpropagate the seismic recorded on the surface to obtain an image, and pre-processing, which is mostly about denoising. Again, I'm simplifying here a little bit, and I've circled a few things which I believe are a little bit more practical. Now, for interpretation, the picture is a little bit more mature, I would say, in terms of things that we use in everyday life. And there is a number of areas where these methods help. For example, fault detection, phase shift classification, geobody identification. Just remember, I pointed out some of these things in my first slide, just to let you know how they look like. And I would say more of these things are probably practical today. And the reason they make a real difference to our lives is because they help us automate very labor-intensive and repetitive tasks that humans otherwise would have had to do interpreting those seismic images. And that makes everything faster. So that will be a recurring theme in my presentation. Next, I'm going to hit these 4 different areas or types of machine learning applications. That will be computer vision. Then I'm going to talk about regularization and uncertainty quantification, which I think Biondo mentioned this morning in his keynote presentation, information transfer between different types of seismic and non-seismic types of data, as well as a hot topic of the foundation models and deciding how similar different types of seismic are. So for the first one, I'm going to call this a computer vision type application. Let's look at faults. These are essentially discontinuities that we see in our seismic images. The problem that we're trying to solve here is that you often have to screen large amounts of seismic data for presence of these discontinuities or faults. And typically, working for a company, the result, we need it yesterday. So there's a lot of time pressure when you do these sort of things. And it's critical in both oil exploration and carbon sequestration. Carbon sequestration is especially sensitive to these faults because, as you can imagine, if you're about to inject CO2 into the subsurface, you want to stay as far from these as humanly possible because they present a possible pathway for your CO2 to escape and go back into the atmosphere. So you try and screen your potential areas where you're going to inject for presence of these faults and basically not go where you see them. What you'd like to have is a tool for replicating what an interpreter, what a human is thinking, based on just a few examples, and allow them to test different scenarios. And the solution, and you'll see again, this is going to be a recurring theme. Of course, the solution is to use machine learning, right? We can train a 2D or 3D neural network based on interpreting typically just a few inlines and crosslines, which means a few of these vertical slices. And then you train a neural network. And for this application, the simplest one, like UNet, usually does a great job. Ideally, it should be 3D, but it turns out even a 2D is fine. And people are doing this on commodity GPUs, and the single V100 GPU usually is sufficient. And I've seen publications which claim they can do it on a $800 laptop from Costco, and it still works just fine. Slightly more ambitiously, let's look at the task of identifying more complex geobodies like salt. This image shows in red a salt body which is colored inside the seismic image. And we typically want to see its top, which is shown here in blue, its base shown here in green, as well as a mask which identifies the geobody as a whole. And the reason we need it is because some of our geophysical workflows require us to have that as part of solving that complicated inverse problem. Once again, the task is to automate automate things and minimize human input or amount thereof, and then output these top base of salt as well as the whole body. So the solution is that because you want several things at the same time, you apply a multitask learning method, where we first put together a typical encoder-decoder structure which learns the structure of the seismic, and then once we have developed this so-called latent space and extracted salient features from the seismic, we train a number of downstream decoders which then output what's that we're looking for. So this is, in fact, considerably more challenging than the previous task because salt bodies are inherently large scale and have very 3D nature. So this is where having more memory available to you, either through a hardware solution or a software solution, becomes very important because otherwise the results often come out suboptimal since you have to deal with one 2D slice at a time. The next type of application is based on figuring out how different types of seismic are similar to each other. As we all know, neural networks are really good at identifying what's similar, what's not. That's how Amazon suggests to you what else you should buy based on your previous purchases. This is no different. It works exactly the same way. And the way we apply it for noise attenuation is we first extract these salient features. In this case, we use the Siamese network for this purpose. And once you have the latent space where these salient features have been extracted and the network has determined what pieces of the seismic that are similar to each other, say these 4 rectangles up here or these 3 down here, as well as figured out which pieces of the seismic are different from each other, you can stack them or sum them coherently, thereby attenuating the noise. And you can see that from the noisy picture up on the top, we obtained the one at the very bottom, which has removed a lot of that noise and in fact performed better than a conventional method, which still had a lot of this dipping, cross-cutting noise left in it. That's the middle pair of figures in here. So it helps. And once again, this becomes slightly more computationally challenging because you would like to understand the nature of the seismic in 3D as opposed to working in 2D vertical slices as shown here. You can get even more ambitious in utilizing the same idea and try and put this in reverse in the sense of attempting to minimize the HPC or computational requirements for a particular technique. So multiple attenuation is a good example. Here's an example of seismic data, and you can see that down below in this bottom portion of it, you have a lot of intersecting events. And the reason is that there are a lot of these so-called multiples shown separately in this bottom picture, which are the waves that bounced up and down a few times. Therefore, they arrived a little bit later in this section. You want to get rid of them. They're not good for our conventional imaging techniques. So conventional seismic processing methods are very effective at accomplishing this task, but they're also incredibly computationally intensive. So as far as HPC applications go, this is one of the more computationally intensive tasks we do. So how can machine learning help? Well, what you can do is replace these traditional methods with cheaper and more automated techniques. All you do is create a bit of training data, which looks more or less like your field data, and you train a neural network to perform this same task based on those few examples. The trick is where do you get the training data from? This is an example of how you can mitigate the absence of large amounts of field data sets for training, which is a little bit of a curse in this type of applications for seismic. Typically, you never have enough field data to train your neural network. So how do you generate synthetic that looks like field data? Well, in this case, it actually turns out to be possible. You just make an image out of your field data, doesn't matter how good it is, and then you perform a forward simulation solving a partial differential equation, which allows you to model these multiple reflections which bounce up and down several times separately from the ones that reflect only once. And now you have yourself a very nice training data set that is almost indistinguishable from your field data. And with that, we utilize our usual trick. We do an encoder-decoder architecture, and we separate things in the latent space. So this becomes even more computationally demanding, interestingly, than the previous task, because we know from the physical considerations that you need to look at a lot of this data simultaneously. And now we're talking about terabytes of data that needs to be consumed and viewed by the neural network, preferably at the same time. So once again, either a software or hardware solution that is conducive to that is most welcome. Otherwise, the outcome is likely to be suboptimal. However, that said, once all is said and done, the computational requirements for machine learning methods are less than they are for conventional techniques. And I've seen some companies who may not potentially have a large HPC in-house utilize these sorts of methods to get a quick result as the data are coming off the boat. So it just allows you to get a first look at the subsurface faster. Another interesting type of applications is transferring information from one type of the data to another. In this case, what you see in the picture is looking at the data that has been recorded in a borehole, that's the hole that we drill in the ground, and that's usually understood to be the ground truth, to the seismic, which covers a lot of the surface, but from which extracting information is considerably more difficult. So what you want to do is you want to train a neural network at one location. In this case, we were going after identifying carbonate presence in the subsurface, and then apply that throughout your seismic section. And as the results here show, what it typically gives you is an alternative to physics-based techniques. So there are physics-based conventional methods that are computationally expensive, and machine learning is able to replace them and give you perhaps a different scenario, which is what ML often excels at, producing different scenarios that are consistent with the data that you have recorded. Once again, getting more ambitious with this type of applications, let's look at another problem of bandwidth extension. The problem here is that conventional acquisition with boats, which is what I showed in my first slide, often lacks low frequencies. That's just how the hardware is made. It's difficult to have low frequencies recorded when you have a streamer acquisition. On the other hand, this ocean bottom acquisition, schematically shown here, is reaching these low frequencies. Unfortunately, it's also very expensive, unlike the streamer acquisition, which is much cheaper. So what you're tempted to do is to have a small amount of this high-quality data over a given area and learn from it how to reconstruct these missing low frequencies in your cheaper data, which covers the whole area. The principle is going to be very similar to my previous slide. You would train a neural network using the expensive but sparsely available data, just like in the previous example, and then apply that learning to your cheaper data, which covers your whole area. And this example just shows a few of those short records, which I showed in one of my introductory slides, where we compare how their reconstructed low frequencies or enhanced one shown here on the right compared to what was present originally in the data. And what it does for you, it allows you to form a better image with enhanced low frequencies as shown down here. From the computational standpoint, this is again incredibly expensive because now you're asking the neural network to learn implicitly about the subsurface structure of a large geographic area. So it needs to see tens, if not hundreds of terabytes of data, again, simultaneously in order to ingest all of that information. And of course, the application of these methods needs to happen relatively quickly as well to a large amount of seismic data. So this becomes very computationally intensive. I think Beyonda has already mentioned this type of applications this morning, which is regularization and uncertainty quantification in inverse problems. In fact, I stole this diagram from one of his papers, so that may look familiar. Conventionally, what you do when solving an inverse problem, you solve a PD constraint optimization. You formulate it as PD constraint optimization, and there are well-known solutions to that. This is incredibly expensive, and especially when you go elastic, and it justifies huge HPC facilities just on its own merits. But unfortunately, it doesn't allow you to do much of scenario testing because it's so expensive, and it suffers from local minima and inability to quantify just how good your solution is and what the range of possibilities is that's consistent with the observed data. So the solution, of course, is to train a neural network which generates models consistent with a given set of geological scenarios. What you can do is you can use a different methodology to generate scenarios which you think are plausible. Then you train your neural network, some generative system. It can be diffusion, it can be a GAN or anything else. to produce models that are consistent with your preconceived notions about the subsurface, and then you fuse that sort of machinery with the one that performs your physics-based optimization. This, to me, essentially squares the HPC requirements because you're fusing an incredibly expensive physics-based method with an equally expensive, potentially machine learning algorithm. Now, there are caveats to the statement that I just made, but this is what's keeping perhaps some of these methods, however attractive they are, from being part of our everyday workflows. It's just very difficult to implement and run them efficiently. However, if we were able to do it, it's literally one of the few approaches to quantifying uncertainty and regularizing nonlinear inverse problems. Now, moving on, here is a way to put all of these different pieces that I have described together. And that has to do with the so-called foundation models. This is, once again, very similar to what people at OpenAI do when they take all of the internet and pour it into one big neural network. What is done here is the moral equivalent. You take all the seismic data that you've got and you pour it into that neural network and force it to extract the same salient features. And that's typically done with something like a masked autoencoder, where just like with ChatGPT, where you remove parts of the sentence when you train the neural network and force that transformer to predict the missing part, you do exactly the same here. You cut out a little piece of the seismic and force your transformer to predict what's missing. Once that is done, you can now much quicker do the so-called downstream tasks, which can be any one of the ones I've described previously in my talk. And the upshot is that now you have to prepare a lot fewer of these training examples for this to work well. Now, in my opinion, this is still an emerging area, and while papers have been published on how effective this is, we still need to ascertain that that is really the case and which applications really benefit. As far as computational requirements go, this becomes very compute intensive. One recent paper quoted, I believe, 1,000 GPU days on A100 GPU to train a fairly straightforward version of one of these foundation models. And we're just getting started because we'd like to have a lot of channels and other things that play into it. And finally, getting really ambitious, that's my last example. What you really want to do is make your neural network think like a human. You'd like to put together these different individual pieces that you may have predicted using one of the methods I've described previously. Put it all together and tell you, for example, either where the hydrocarbon accumulations are or where you want to be injecting your CO2 into the subsurface. And for that, you need to understand the geology, different components of it. The way to accomplish it potentially is to utilize one of these graph nets, which I'm not an expert on, but the idea is that you represent each piece of geology as a separate node in that graph, and then the neural network is able to reason as to how the combination of all these pieces of information put together, potentially different pieces of information, including language data, what does that tell you about the presence or absence of hydrocarbons or suitability of a particular location to CO2 injection? Now, trying to think about the common technical challenges that we encounter while applying all of these methods. To me, again, looking at it from the business perspective, one of the key ones, maybe a little bit counterintuitively, is finding the right application that make the most difference. Often we focus on applications that seem to work, but really they may be speeding up an isolated step in your long workflow, and that does not justify the effort a lot of the time, no matter how nice the method looks. On the same note, integrating these machine learning methods with existing workflows is a huge challenge in the industry, because having a standalone tool, a nice hammer that can solve one problem, is not helpful. It needs to be integrated with the other tools that you have at your disposal. Creating training data in sufficient quantities, I have already mentioned that earlier. It's often very difficult to have a sufficient amount of that for your neural network to generalize well across multiple data sets. And explainability is a huge challenge as well. For whatever reason, our managers like to know why a particular decision was made. And it's very difficult to explain why a neural network arrived at a given prediction. So explainability would certainly help a lot in acceptance of these methodologies. And the take-home messages that I really want to leave you with is that, in my opinion, deep learning is already making a huge difference today. It's faster a lot of the time than conventional methods. It automates a lot of repetitive tasks. It turns out to be better than conventional methods because it can simultaneously take into account multiple aspects of your seismic, which is very different for a human brain to do. And the ideal application is where you need an imperfect solution quickly. This is where these methods really shine. If you need an absolutely perfect solution, this may or may not be the tool of choice. But hopefully it can make an even bigger difference in the future, because it seems to be a viable, or maybe the only viable path for scenario testing and uncertainty quantification in these complex nonlinear inverse problems. It perhaps can help you have this holistic understanding of different types of data, which again, for a human is different to achieve. And what I've left out of this talk, but I'm sure it's coming, is integration with large language models can lead to really a paradigm change where we just interact with our seismic in a totally different manner. There have been some publications recently on that as well. With that, I just want to acknowledge some of my colleagues, and thank you everyone for listening.